I am Loki, and I am on a journey to master reinforcement learning. In this series of videos, I will share what I have learned so that anyone interested can learn along with me. In this video, we will get an overview on what reinforcement learning is and how it works. So, what is reinforcement learning? Simply put, it is learning by trial and error. The program or agent learns by interacting with the environment. As part of the interaction, it receives a feedback signal or reward, which tells it whether the action taken was good or bad, and this forms the basis of learning. The agent starts in a state st, takes an action at to reach the next state st plus 1, and receives a reward rt plus 1. As we will see later in this series, it is possible to learn incredibly complex behaviors, all starting from the simple idea of trial and error with feedback. How is RL different from other kinds of machine learning? On a high level, machine learning algorithms can be divided into three major categories. Supervised learning. You can think of it as learning from examples. Let us consider the problem where you want to teach the program to correctly classify a given image into a cat or a dog image. To do this, you feed the program a labeled dataset of lots of dog images and cat images. By going through the examples, the program will learn to correctly classify a given image into a cat or a dog image. Then there is unsupervised learning. It works by finding hidden patterns, associations, or clusters in unlabeled datasets. In the previous example, if I give a set of unlabeled images to the program, it can group the images into cat and dog groups by identifying the cat and dog patterns or features. Of course, it won't know that these are cats and dogs because they have not been labeled as such. Another example would be creating customer segments based on their purchasing patterns. So what can reinforcement learning do? It is learning by doing. Let us look at some of the examples that reinforcement learning can solve. A robot learning to walk. The longer it walks without falling, the more reward it accumulates. A program learning to play board games like chess, shogi, go, or even complex video games like Dota 2. Reward is the score of the game as dictated by the rules of the game. A program learning to balance a card pool, which is a classic example of a class of problems called optimal control. The longer it stays upright, the more reward it accumulates. Typically, we can use RL algorithms for any problem where sequential decisions need to be made in order to maximize the reward over multiple time steps. A journey of 1,000 miles begins with a step. So let us start with the mathematical formulation of an RL problem. We will be using the framework of the Markov Decision Processes or MDPs. In MDPs, the future rewards and state transitions depend only on the current state and action. Past history does not matter. An MDP is defined by a set of states S, set of all the possible actions that the agent can take, let's call it A, transition function P, the probability of ending up in state S prime if action A is taken in state S. Why probability? Because as we will see in some future problems, the environment is not always deterministic. For example, let us consider a drone trying to navigate in a certain direction, but there is an intermittent wind in the environment which changes the direction of the drone. Reward function R, the reward you get when you end up in state S prime by taking action A in state S. Discount factor gamma. This is a measure of how much more we value immediate rewards than long-term rewards. The first reason is the intuition that because the future is uncertain, immediate rewards must be given a higher weight. Another way to think about this is, like the same amount of money is more valuable today than 10 years later, reward today is more valuable than the same reward at a future point in time. Hence, future rewards must be discounted to reflect this. The other reason is that it happens to be mathematically convenient for the solution to converge. Time horizon h, the time step one looks up to in a forward view. Or in other words, how long the agent is going to be acting. When solving for an RL problem defined by this MDP, we want to define a policy pi, which is the agent's strategy or rulebook for choosing an action in a given state. A policy can be deterministic or stochastic. Why stochastic? Stochastic policies can sometimes allow us to arrive at a more optimal solution or get there faster in some cases. We will cover this in more detail later. The goal of the policy is to maximize the expected total discounted reward. If we can map our RL problem to an MDP, we can then apply a bunch of cool algorithms to solve it. In the next video, we will apply what we have learned here today and solve our first RL problem. If you found this video useful, please like, share, subscribe.